Thank you. I'll try to keep this as short as possible. There is going to be some overlap of ideas from here and tomorrow's keynote just because of the domains. My name is actually Cecil Joe. I speak very little Spanish. Sé un poco de español. I don't know how many of you are speakers of Spanish. You know, I used to hang out with students from Mexico and Puerto Rico and picked up some what I thought was good Spanish. But anyway, I can make do if I go hungry in Madrid maybe. So very happy to be here. We are part of a new interdisciplinary center at Oklahoma State. My background is from mechanical engineering, then I became an industrial engineering faculty. And then more recently, I'm now in the computer science department to co-direct this interdisciplinary center in cyber-physical systems. My background is predominantly, at that time in the 90s, I worked with a very famous professor who came from industry called Richard Meyer, and he was one of the few who focused on design of software systems for engineering applications. Until that point in time, right, if you had to build the software systems for manufacturing, you would go to this computer scientist. And computer scientists, no offense, I'm currently classified as a CS, really don't know much about actual real world systems, right? They don't understand the intricacies of a process. To computer scientists, a program is a program, so what's the big deal? But the reality is the IT industry has close to 50% of failures. This is not a well-documented fact. And the main reason for this is the lack of the interdisciplinary focus and the lack of understanding of the complexities of mechanical systems. So our center, as you can see some snapshots over here. We focus on cyber-physical systems with a large degree of reality, even though we are part of a virtual reality center. My domain of emphasis today is on a very advanced area called micro devices assembly, right? Now, those of us who remember our math, a micron is 10 raised to the power of -6. It's very small, right? Size of a human hair is about 80 microns. So why did we choose this discipline? Well, I was before at New Mexico State University, and we started working with the world-famous Sandia National Labs. They were interested in manipulating micron-sized sensors for a number of applications that I really can't go into, that you can guess by itself. And our interest was, if you gave me a very advanced design, let's say a chem lab on a chip, right? Some crazy guy comes to New York, goes to Tokyo, and tries to contaminate people, you may have to assemble these sensors very quickly, very rapidly. Large volumes would be 100 or 1,000, right? This is what we were interested in. And we said, can we use an assortment of cyber-physical resources, could be different parts of the world, can they come together and rapidly assemble them in a very real-world response? So for this reason, we went about this project. This was one of the few that was indirectly funded by President Obama. It's part of what we call as the Next Internet Initiative. So what we built does not use the old internet, but the new internet. Most in manufacturing and even in engineering are not aware that the old internet is being phased out gradually. And this is one of the pilot projects that benchmarks not only how to design such a system, but also benchmarks the performance of this emerging internet technologies. So my co-authors, my graduate student who graduated, but he can't travel for a number of reasons. We have an interesting entity in our president, and so if he crosses the border, he can't go back into the US. So he stays over there for a number of reasons. So I am talking for him in many ways. And my collaborator is a well-known guru in IT, Professor Ramanathan from Wisconsin-Madison. He's a networking guru by itself, and I'll go about describing our main findings. So I'm going to briefly talk about ICE, then I'm going to go into IoT and CPS. We'll talk about the nuts and the bolts. What did we design? What did we build? What are the challenges? And then we go towards, what we call as a GA-based planning approach. Our focus, as Professor Rai mentioned, it's not about getting a perfect solution. We are happy with a dirty solution. Those of you who are great at optimization, you may have a better approach than ours, but this works, and it works fairly well. And then we'll talk about the next generation computing. This is my co-PI's work. I will try to do my best to explain what he gave me an overview about the next computing set of principles. So by itself, I'm going to focus on something called design of a process. This has been ignored in the IoT and CPS communities. People have CPS papers, they talk about feedback, they talk about embedded systems. But how do you design them? It's messy, it's not easy, but I'll use some of my perspectives to share what we have found. We do want to underscore the importance of what I call as the ICE principles. This is the basis of collaboration, right? It's all about data, information, and knowledge being exchanged. And I'm going to share how we apply this to create, this is arguably, and I say that arguably with a pinch of salt, the first comprehensive living testbed for advanced manufacturing. We have tested this from different locations, including our collaborators at Exxon Provence, so it works fairly well. Now, I'll be preaching to the choir. Many of you have seen variations of this, right? Cyber-physical systems. When I started my work in Sandia, we had intended not to build a complex system. We had wanted a system where some Sandia researchers could access our physical assembly tools without our presence, assemble something complex from different parts of the world, and go home, right? That extended into this massive beast. Our work predates the emergence of IoT and CPS. But in a nutshell, this is what it is, right? We have the need to use distributed resources. These resources could be, anything from a thin client, could be machines, could be robots, right? So the cyber aspect is fairly straightforward, right? What can I do in the cyber world? I can do planning, I can do scheduling, I can model, I can do physics-based, but what I don't want to do is the Walt Disney cartoons, which shows up on CNN and Fox, right? Because if I'm trying to build something complex, I need to have a realistic, not the 2D-based CAD/CAM systems, which are predominantly the norm, but physics-based 3D environments. We'll talk about the challenges, and I think academia needs to take quite a bit of the burden for not moving away from 2D, but towards 3D, right? If we are going to be, so-called precursors of the Star Trek generation, where you have these holographic images, professors need to get interested, teach the students the nuts and the bolts, so that we will have meaningful tools that interact with us in a three-dimensional environment. But this has been a problem, and we'll talk about some of these challenges. So when you look at the elements, right, when we design something, we got to worry about the design of the cyber components, the interfaces, the physical components, the feedback components, as well as all important networking capabilities, because my resources are distributed. You know the term IoT. They're both related in many ways, because when you look at what the IoT is, you have so many definitions. I stick to the basic. It's still, for me, a network, right? It's an internet of something. It can be complicated. It can have a human interface. It doesn't matter, right? By itself, the intention is to have data exchange shared very seamlessly across multiple platforms, right? If I have a cell phone, and if I was, let's say, the manager of a plant in Ohio that was building something, right? 2 hours before a breakdown, if my simulator tells me that CNC machine is going to break down, what does IoT do for me? Or what should it do for me? It should give me an alert to predict that something is going to happen, and having access to the cell phone would mean I can either call the shop floor supervisor or try to preempt or prevent something, right? So IoT is not the panacea for everything, but it provides a very logical context for exchanging data that can provide value. Today, everyone jumped onto the bandwagon of IoT without realizing, is this going to be useful? If you're a small company, and you don't want to share data, and everything is just co-located, and you don't want to have an advantage over your competition, don't get into IoT. Most organizations today want to get into IoT because it's the next cool thing, but that's not the overall, or should be the overall motivator. So the challenge is then is, how do you build such a complex framework, right? You're dealing across levels of platforms, you're looking at very complex software-based interactions, that's number one. The second one is the current internet was not designed to handle the complexities of today. That's why in the US we have the Genie initiative. In Europe, you have a lot more funding than us. Those of you from Europe, go to your Horizon 2020, get into partnerships. There's a large number of projects depending on validating this next generation of internet. The first internet was an accident. That's how it happened. And then everyone started using it. The next generation, we want this to be designed. So engineers need to work with computer scientists. It's not a black box, to work on issues from latency to gigabit, exchange limitations, which are extremely important. And of course, I'd like to thank those who gave us the funds. Without funds, we really can't do a whole lot. We've had 6 or 7 grants from NSF, several from Sandia, there's Los Alamos National Labs, as well as the Mozilla Foundation. So my scope, I've already talked about this very briefly. So what I'm going to focus on is, the cyber-physical elements. And our context was very simple. I'm sitting on a beach in Hawaii, and someone emails me a design, a micron-sized design. Using our approach, our goal was, give me the design details. It'll go through a life cycle, and it's going to tell you, can I build it or not? And if it can build it, it'll build it. Okay, so that's why it's very groundbreaking in many ways, and without the interdisciplinary team, obviously this is not possible. The cyber elements has to do the assembly planning, yes, good old planning. You also have path planning. And then we have some advanced multiple simulators where we can predict what can go wrong. I won't cover everything. We have other papers that discuss. There's a very pesky force called van der Waals. When I was in high school, my physics teacher told me, don't worry, gravity dominates. Ignore van der Waals. Guess what? At the micron level, van der Waals dominates, right? So you can pick up an object that happens to be several microns in size. You can't release it. So we studied insects and we figured out a way to try to mitigate it. We have not eliminated it, not yet. One of my students, may win the Nobel Prize. I tell them if they come up with a faster method. The physicists argued they've resolved the problem of van der Waals. And then as engineers, we went in and we looked over the derivations. Not true. The way the physicists do is they could not measure and validate it using realistic approaches. And that's a major problem in engineering. Then we'll talk about the interface of physical equipment. And then we perform the assembly, and then how we use camera-based feedback for a loop to be closed. So anyway, most of you, I think, like I said, it's assembly of micron-sized parts. The first time I saw someone assemble something, it was a human operator. And then he lost his concentration. He dropped this micron-sized part. I didn't even know what he was looking for. He spent around 5 minutes trying to pick it up. So the first time we shopped around for funding agencies, they said, well, what's the problem? Ship the design to Malaysia or China, they'll assemble it. Guess what? They can't do it, right? You're going to spend a whole lot of time. Probably a little bit more suicides will probably happen. You get a headache and something else. So we have no other choice than to have computer-assisted assembly methods, right? Automation, full automation or partial automation. In microassembly, we turn the challenge to our own, benefit, because there's not too many organizations that can assemble micron-sized parts. The entire market moved from micro to nano. Everyone said there's lots of parts in nano. But we said we're going to stick to micro because we had industry partners who wanted things done, right? So when you have expensive resources, Gone are the days that companies are going to have these massive CNC factories and these shop floors. That's gone forever. The economy is not coming back. We got to figure out a way to deal with a customer who wants low volumes of parts, whose design requirements, as emphasized in the keynote addresses, said are always going to change. So you're going to have to figure out how one day I'll be making chairs, 6 months down the road I'll be making something else, right? And there's going to be 2 new market leaders getting into your domain. Think about Apple. 20 years ago, could it have been imagined they make cell phones? So there are no longer, preeminent leaders in any manufacturing industry today. You better be ready for an outside threat. If you're not information-centric oriented, your agile response is gone for good. Always think about Nokia, and of course, I forget the other group, BlackBerry, in there. Right? So for our design process, we built what is called an information-centric modeling process. This comes from Richard Meyer's way of looking at things, where you have to establish the functional relationships and temporal precedencies, right? Gone are the days where we had James Bond with his $3 million or $30 million design, trying to jump over buildings and get the product design. Today, it's the process design. If I have the process design, it's a lot more valuable than the product design because it tells me how I can use my resources to build something. Who cares if Chevy has a great set of 15 different design features? The Chevy is not as good as the Toyota. It's because the Toyota as an organization focuses on process design, not about, can I change the vent automatically or something else. And we used an evolving modeling language called EML. You can use any other modeling language. You can use UML's activity diagrams. There is, I think, BPL, which is very popular in Europe, for instance. But at the heart of this was the classification of data and information, because we needed a life cycle model that would tell us, at which point in time do I need what information, and what are this classification of data, right? If I'm going to assemble something, I need to know the constraints, the schedule, which might come through the web from somewhere else. I need to know which equipment is available for my cyber simulation, as well as my physical reality. I need to know what inputs I would need, and I need to know the software elements. The humans, the voxel, the computer-based programs, and most importantly, the most complex are the decision outcomes, right? At every stage in a manufacturing process, there's a plethora of information. This is where computer scientists fail because they don't understand the relationships between data among the functional dependencies. And that's why Windows gives us a lot of problems, because it's still a very CS organization where they don't have enough use case scenarios that flesh out the details and say, these are all the possibilities. And until they fix that, Windows is still going to operate at a very, not very satisfactory level. So these decision outcomes, these are the hooks that another keynote speaker talked about, right? When I finish something, whether it's a cyber task or a physical task, I have new data and information. Something is created. Does this stay with me? Do I keep track of it? Do I send this somewhere as a feedback, right? So it's almost like a very complex state chart, right? And when you look at the older PetriNet models, it's an extension, because I worked on PetriNet related projects, and I said I'm going to extend this network. It's very complicated, but at any instant in time, I will be able to tell you what new information is obtained, what's being generated, or did something else go wrong. I think I'm really running out of time, so this is a...
Take your time, sorry. Just take your
I can take my time? All right.
Just go ahead. Yeah.
Okay. So this is one of the process maps for IoT. I'm showing you the top level decomposition, and we exploded each box so that we know all the relationships between the entities, right? So if you start from this side, right, I've got to receive the target design from my cloud or whoever is going to be uploading. I got to generate the assembly plan, generate the part plan, perform the simulation, again distributed users, assemble the device, and then of course keep the team posted. This is an elided model. The actual model is very complicated. It looks like a, a hybrid octopusian model. I've taken off the feedback loops. But here it tells us, what are the main responsibilities of the various software as well as the human components. Are we going to the next? So this is, something happened. All right. So this is a test bed which is running on a cloud server. This is a Genie-based server, which I'll get into it later. So we have from design analysis to assembly planning, monitoring, VR-based simulation. And then we have physical microassembly work cells. Users can access it from different locations. And it goes through this cyber-intensive cycle. What I've not shown is the cyber-physical manager that coordinates the interactions among these entities. I think this slide was there by mistake. Anyway. So we had 3 categories of algorithms, and the main reason why we had this is we adopted the virtual enterprise model where I could have Boeing doing one kind of assembly based on their own algorithm. I could have maybe Airbus on different algorithm. Bad analogy, but gives you an idea. And maybe another group in China. China is trying to start creating airplanes or rather building airplanes. So we demonstrated that you could have many different algorithms. How do I know which is better? That's still the problem, right? We run them through our simulators, we validate them, we compare. Now, if you're going to ask me about merit and trust, that's complicated. We'll address that later. As of now, our tie was broken by least assembly time from the algorithms and the lack of collisions between the various devices. So there are many steps. The main step is this. We generate a fitness function. Those of you from industrial engineering, you know what it is. We had operators. We proposed a few ones because we still needed academic relevance for this. So we proposed new operators. Then you generate new children sequences, and then you keep rerunning the sequence until it comes to what we think is a near optimal solution. We were not interested because it's an NP-hard problem. We're not too focused on the optimization by itself. So here you see one of the sensors that we are assembling, using this gripper that we have. And here is, of course, a more theoretical layout on how we modeled it and how we went through the various steps. Again, we generate new parents for the sequences using chromosomes, right? And we use the crossover operator where you basically split and you merge. We call this genetic algorithm because the overall idea is this is how human relationships and DNA is passed from one generation to another, right? So when you compare my DNA with one of my ancestors, there's going to be some semblance of resemblance, right? But some of my ancestors who will succumb to a disease may have passed away, and they may have some traits that are not considered great. It's not the best analogy, but it derives it from the field of biology. So mutation is as well, where occasionally we can take a good sequence, right, and then we jiggle it or juggle it, and it's possible we might get the better or the more improved answer. So we do this randomly until we get the better answer. There are other groups who keep on looking for a better answer, but the key is you might get stuck in a local maximum. So we make sure that we don't get stuck in that situation by using a variety of operators. The algorithm is fairly complex. Main steps start out with a random number of random sequence for the n number of parts you need to assemble. Compute the distance value, generate the children sequences. We have different heuristics. The 70% from crossover and 30% from mutation worked well. They become then the next generation parents, and then we continue to repeat this until we are pretty sure we've reached the near optimal. So the VR environment, I have to really thank my students. We have spent hours, days, months, and years, and we are one of the few groups. We wanted our environment to be as close as possible to the reality. So here you see one of the virtual environments, and here you really can't see it too well, but that's one of the feedback loops coming in from the physical system. These micro-assembly environments we have built from scratch, so out of maybe the 30 work cells in the world, we have about 4 of them. So the area, the real estate is very small, right? So it's roughly by 2 inches by 2 inches if I ignore depth. So we have a gripper where we can change the grippers. In a different paper, we studied van der Waals modeling, and our gripper has something called a sawtooth surface, right? So what do we do as engineers when we don't have enough funds? We try to, hit our heads on the wall, shake it a bit, and we talked to Sandy and we said, see, when you're gripping something very small, if I have a flat surface, I have a good gripping force. It's not going to slip, right? But my van der Waals force was going up, so sticking was occurring. So we looked at the insects. They're pretty smart, right? They got 1 million hairs in very small areas, clamber up walls. We don't fully understand how the insect is able to yank its leg up, like a gecko does, and clambers it. We know there's some magic in there. But we said, we'll take that idea and we'll reduce the number of contact points. I would have liked to have 1 million hairs made that I could control, but my program manager said there's not enough funds for that. So what did we do? We came up with a pyramid structure, the sawtooth, triangulation, right? And we said point of contact will be just a point, right? But I still have relative gripping force. So this gripper has worked fairly well. We showed in different papers the theoretical as well as the experimental results were able to be controlled fairly well. So here again is a snapshot of this. And the original simulation was running on an expensive $250,000 Powerwall. But these days they have the $700 wire. Resolution is bad, but cost is good. The manufacturing community can actually use it. We will talk about this tomorrow briefly in the keynote as to the next era. Here are again snapshots of our work cells, taken from different angles as we went around doing this. We also piped it, through the cloud so that people on YouTube can actually follow process or assembly steps. So here is the older semi-immersive Powerwall. It's a little bit blurry, because it's showing you stereo vision, right? So when you wear the eyewear, the blurriness disappears. There we go. Here again, more snapshots of our robotic work cells. They do an assortment of different ranges of tasks. And here again is a side-by-side comparison of a virtual and physical cell, which can be accessed through this newer internet. I've given you other examples over here. So on the van der Waals modeling, I'm not going to go into great detail. There's a large number of slides over here, and I have to admit, this seems to be happening with me fairly well. I had deleted these slides, and there should have been another file, but I think I copied the wrong file. Okay, but anyway, this will at least give you an idea that I think I must have got the wrong flash drive. But anyway, so we have 3 components: the surface tension, electrostatic, and van der Waals, right? Again, I'm not going to go inside it, but this was the overall, shape that we had manufactured, and it's really difficult to, to manufacture at this scale. But Sandia National Labs was very kind enough to machine this for us, and so we had very good results from this. So anyway, so let me talk briefly about the next generation internet, right? This is a collaboration with Wisconsin-Madison with Dr. Ramanathan. Just like the term artificial intelligence, sometimes people in the US government, they come up with these names. See, the name they came with was GENIE, the acronym. Promises a lot, right? But actually it stands for Global Environments for Network Innovations, right? And so there's 5 major countries involved. There's the US, there's Japan, the EU, if we view them as a single entity, and we have Korea and Australia, as well as China. Okay. So the overall idea was the current internet is too many patches. It's on its last legs, it's dying. People use it for all kinds of crazy applications, So, but anyway, we can't blame anybody for it. So we wanted a radical design. So the overall idea, the most innovative aspect is something called software-defined networking, right? So today, the current internet, I go buy the router from Cisco or someone else, I can't mess around with it. The router controls everything. With SDN, decoupling the hardware from the software. The software becomes a network decision maker, controls the way data can be exchanged. So in moments of national emergency or like in Oklahoma and we have tornadoes, we want first responders to interact, we can do a little bit of control over that so that the data exchange can occur at the speed that it's supposed to. And more importantly, again, this is not my area, what Dr. Parmesh has given me a tutorial on, can do load balancing and distribute the traffic more efficiently to prevent choke points. So this is a big deal, the new internet. So this is again an overview of the architecture that we've interacted over here. There is something called OpenFlow. It's an implementation of SDN, and we have just shown how users can interact from different locations. So what was interesting was, again, with the help of my computer science co-PI, he had, we collected data and we demonstrated the non-haptic interactions, the latency was fairly stable at 46 milliseconds, So the overall idea is this, rather the hunch is, doesn't matter how smart we get, how fast the internet is, latency is going to be a characteristic of all networks, right? I think just like the way, I think it may have to do with the way we humans interact. The network and everything that we're involved in, there are some attributes from our human behavior that somehow get reflected on the artificial aspects of anything we create. So one of the philosophical arguments is latency is the way some or most human beings, it's part of who we are. So whatever we design is going to have that inherent in that. I can't argue with that, I'm just quoting what one of my peers said. Then we also have haptic-based interactions where we have low-cost, haptic devices. They're not the higher end. These are the $1,000 machines. They're slightly higher at about 48 milliseconds. Right? Tracking is the most confusing, most difficult. We've had several students, work with me on this. So the overall idea is this: we took the design state chart, right? We broke it down, and as the various activities progress, we monitor them and we see, is this going according as planned, right? We don't have the perfect automation like in Toyota where we can stop things, but if accidents are going to occur, we do stop them. So overall, the tasks would be, get the user's design, if there's problems, let us know. Assembly planning, same thing, there are 3 levels of decomposition. Generate the path plan, perform the simulation. If things don't work well, I've taken off the feedback, then go back over here to assembly plan, or if we're not able to assemble it, go back and tell the user, we failed. And then we use the intermediate generated data to physically assemble them, and then we project the data onto the cloud that keeps track of the assembly status, as well as keeps my enterprise manager or my cyber physical manager in the loop. So another snapshot of the same thing, just to give you an idea of the complexity of data. So when you look at these work cells, right, the inputs are, I need to know the assembly plan, the path plans. Another caveat was, even though we have different controllers, we have code generation mechanisms based on the simulation that will generate efficient code to control these robotic controllers. So that's the inputs coming in. Coming out, the camera keeps track, actively of major aspects in the assembly from, the camera, the gripper position to, the status of the assembly plan. So it can tell me exactly what status has been completed in the part placement, the gripping details, the micro positional movement status, as well as overall assembly tracking, which again goes through the cloud and makes sure everyone in the loop are in the know. This again, a different view, and we showed colored charts to tell you that what could be the status at any point in time, right? So it could be, it's completed, it's a green, if there's problems, there's red, yellow is a work in progress, and then you have, again, green, well, the color got a little bit messed up. It should have been black over there. I must be getting colorblind, I think. Anyway, top level tasks, and coming towards the end over here, so we have a very advanced, design system using collaboration diagrams. I may not have time to go over the semantic framework itself, so it's a different paper at a different conference, but a bigger problem was when you use multiple software tools, different languages, different platforms, the often ignored aspect is semantics, right? So we address them using building an ontology. The problem with ontologies is it's a very challenge. Not everyone can build a good ontology. It's just like design. And here we saw snapshots of some of the parts being assembled. So research summary, takeaway is this, we focused on MDA. General approach can be applied to other domains. In fact, we've applied this general approach to surgical training using IoT-based principles, which my student is going to present. It's a sales pitch for him to put some little bit of stress on it later on. And then the adoption of next generation networking. Discussion is this, we've run through a variety of different tests, predominantly from Texas, Oklahoma, and DC. Then we also went to France and we showed that we can interact. We were able to make an integration between the US and the French counterparts over here. We received a few awards as well along the process. I don't have time for this, but we're using some of these technologies for learning. And what we found out is when you use 3D learning environments, we're able to teach a lot more, and the students' performance actually goes up. So we also have a big outreach program. Do want to thank our funding agencies, and sorry about overshooting our time.
We'll have a quick question, one quick question. If not, of course, we have tomorrow we'll have a complete, keynote.
The keynote, yeah, slightly different area.
Probably the audience probably.
Yeah, we have. No questions. I was that good. No, all right.
So okay, we'll move on to the next.
No, I think Imre has a question.
Oh, okay.
All right. Sorry.
Give me this pleasure to ask a question.
Sorry.
Nice situation. Joe, first of all, very interesting presentation. Really, it's generating a lot of thoughts, in a sense. But there is one thing what I would like to ask, just for my understanding. In which sense is this cyber-physical system concept is different than a sophisticated embedded system?
You mean in what comparison?
What
Which
are
way?
those features which differentiate
mine from what the others? Right.
A cyber-physical system solution.
Right. Just from anywhere else, right? So yeah, good question.
So the
first,
embedded system.
So embedded systems, predominantly when we reviewed them, they focused completely more on theoretical as well as feedback issues. Some practical, not so much. The bigger challenge from that is how do you go about designing them? And our argument is this: the information-centric approach is the foundation. Without that, if you turn this into a feedback or programming problem, you have no clue and you're going to fail. That's number one. The second one is this: most embedded systems use the non-SDN based approach. Okay? Because my co-PA is not there, I'm not able to wax eloquent on this, but that is, I am told, in networking circles, an earth-shattering idea. What this would mean is Cisco's existing routers are going to be pretty much go to waste. They have started building the new class routers. And the big aspect about the IoTs is we are probably the first group that has demonstrated latency at an acceptable level using SDN. All the other groups in manufacturing, not even one has adopted the new internet, and no one has used SDN to our knowledge. We could be wrong, okay? But this is just based on literature. So those would be the takeaways, because the other elements, you can do it using any software by itself, right? And then of course, a big role here is on the VR. It's probably one of the most advanced VR environments where you can interact from different places. So that's all, in some ways, it's a tech milestone, so to speak. So we know this can be done. It's not for toy-oriented simulations, but very advanced simulations that can impact the physical environment. So that would be the three unique characteristics. And that is also something the reviewers asked for, and we were able to go back and do that. Good question. Okay, so those would be the takeaway points.
Okay, the next speaker again.
Thank you.